Okay, in the following example, we are going to determine in a molecule what hydrogens are more acidic and rank them using this tool ARIO. Remember, atom, resonance effects, inductive ACI, and orbital. So here's the molecule. I'm going to draw aspirin, and aspirin is acetyl salicylic acid. And this is the structure. So that's my carboxylic acid. And then I have, now this group is an ester. And I am going to have, say, 3 hydrogens here. You know, it's a CH3, but this time because we are assessing which of the protons are more acidic, I'm going to label them. So we're going to say this is A, and I'm going to label this B. And one of them is I'm going to call it C. So I have 3 different types of hydrogens, and I want to determine which is more acidic in this molecule. So again, to do that, we're going to draw conjugate bases. When I remove the hydrogen in A, I am going to form the following conjugate base. So here you have, just removing that, I created this negative charge, and I'm not drawing the other hydrogen, just drawing the structure of the anion. Every time I've removed, I'm going to draw this as CH3. Is that I only did a condensed form. So by removing hydrogen A, I formed that conjugate base. Now I'm going to remove another hydrogen, and I'm going to remove hydrogen B. So now removing hydrogen B means that I'm keeping hydrogen A in its place, and everything else I'm going to write the same. So I'm going to write this as CH3. And now because I remove hydrogen B, I am going to form this anion. Lastly, I am going to remove the hydrogen here, one of these. And in doing so, let's do it. I am keeping then my carboxylic acid the way it was. I am not touching that. I'm only removing one of the hydrogens here. And in doing so, I am creating, here is a lone pair. Now these are the 3 anions, and let's label those. We said this is A, and this is B, and this is C. So analyzing the structure of the conjugate bases, we see here that this is carboxylic acid charge on an oxygen, and I can do resonance. So here I have, say, the effective atom charge on, I'm going to erase that now. So charge on oxygen here, charge on carbon, charge on carbon. So that's better. So right there, that probably pointing at this is the strongest acid. Also, we know that one of these lone pair is delocalized, and I can do resonance. And that this resonance structure placed in the charge, negative charge here and double bond here contributes the same to the hydrogen. So high contributor. So this is the more stable anion. So that will be the most acidic proton in this molecule. Then I need to analyze this too. Here, the lone pair here is actually localized. I cannot do resonance. And it is on an sp2 orbital. Say, no way I can move that. And so, but on the other hand, if I consider the structure C, the hydrogen C, notice that the pair of electrons here is allylic, so next to a double bond. So I can do resonance this way. And the resonance structure that results, let's throw it over here. It's still keeping my carboxylic acid, everything else the same. But now this has, let's draw that shorter so I have room for that. So I am moving electrons toward the oxygen and putting a double bond here. Those are the resonance structures. So here I didn't have resonance, here I do. And in the resonance structure, my charge is on the oxygen. So because charge on a carbon, same atom, but here I have resonance effects and I don't have any resonance effect. So again, ranking will be then strongest, so more acidic hydrogens are A, and between B and C, C are more acidic because I can do resonance, and B I cannot have. So this is ranking acidity of the hydrogens in this molecule.